Okay, so we've talked a little bit about what aromaticity is. And so I want to spend just one video or whatever talking about what that means. Like, how do we use aromaticity to talk about organic compounds? We know what aromaticity is, right? It's a conjugated cyclic system of pi electrons that has the correct number of electrons, right? And that number is an even number that's not divisible by 4. So, but what does that mean for reactivity? What does that mean for reactions that we can do with these things and all of that? And so we're going to talk a little bit about that, and then we're going to move on to the next thing. Okay, so as we said, one second, I got to turn on my, all right. As we said in previous slides, right, aromaticity implies a lot of stability, right? And so, and then also the opposite is true, right? Anti-aromaticity implies a lack of stability, unstable. So what this means is that if we have a compound that is aromatic, right? I don't know, let's use furan. This tends to be pretty unreactive, right? Because it is stable, right? Furan has 6 pi electrons, right? And hopefully you can see where those pi electrons are coming from, right? You have 4 pi electrons from the pi bonds, 2 pi bonds, and one set of lone pair, or one lone pair, right? And all of these contribute to the aromatic system and make it into an aromatic system. Anti-aromaticity, of course, goes the other way. So if we have something like a 7-membered ring that has an oxygen in it, right, now we've got 3 pi bonds, one lone pair. This is 8 pi electrons. This is very reactive and unstable. Right? So 8 pi electrons, 3 pi bonds, one lone pair. Okay, so how do we use this information? So let's say that we have a compound, right? An example type of question you might see is if you have this compound and you treat it with a base, and you have this compound and you treat it with a base, right? Which reaction is more likely to occur? Which reaction is more likely to occur, right? And up until we started this unit, we would probably look at these and say, well, these are almost exactly the same. Each of these eliminations, right? So these are both E2 elimination reactions, right? We take the hydrogen from the neighboring position and make a pi bond. Each of these eliminations yields a conjugated system, right? They're both secondary bromides. They have an oxygen atom nearby. So everything on these is more or less the same except what the product looks like, right? So the product of this elimination reaction is, of course, our aromatic 5-membered ring, aromatic, right? Whereas the product of the bottom reaction ends up being an anti-aromatic 7-membered ring, right? So the question is, which one of these things is more likely to happen, right? Are we more likely to get the stable aromatic product, or are we more likely to get the unstable anti-aromatic product, right? If we think back to kind of how we've always talked about these things in general, making a more stable product makes a more favorable reaction. More stable product equals more favorable reaction, right? And so the answer to our question would be this elimination reaction is much more likely to occur because the product that we're getting out is going to be much more stable, and that's going to drive this process forward, okay? So in general, we can write down this statement. Non-aromatic starting materials going to aromatic products, this is a favorable reaction, right? So our starting material is non-aromatic, right? We have neutral sp3 carbons here and here. So anytime we have neutral sp3 carbons in a ring, we know that that breaks the conjugation, right? We can't have resonance through there, and so that is a non-aromatic compound. So both of these starting materials are non-aromatic, right? They're neither anti-aromatic nor aromatic because they have those neutral sp3 carbons. So then we look at the products. The product is aromatic or the product is anti-aromatic. In general, non-aromatic reactants going to aromatic products make for a favorable reaction. We can also look at this the other way, right? If we have, let's say that we look at instead, we're going to use the same starting materials, or the same compounds rather. I'm going to take these two things and I'm going to do a hydrogenation. Okay. And so in both cases, we'll just look at one equivalent of hydrogen added, although you may get more than that uh, depending on how this reaction goes. Right, we'll just look at the first equivalent of hydrogen added and see whether that reaction is favorable or unfavorable. All right, so I'm going to add my two hydrogens across the double bond here, or I'm going to add them across here. So now I want you to do the same analysis as before, right? Start with which of these compounds is aromatic, which of these compounds is non-aromatic, which of these compounds is anti-aromatic, right? We have three categories to sort these things into. And then look at how the reactions go and think about which of these two reactions you would predict to be more favorable. So more favorable, which one? Right, reaction A, reaction B. All right, so we already know a little bit about this, right? This is aromatic. It's got 6 pi electrons. This one is anti-aromatic. It's got 8 pi electrons. And then these are both non-aromatic because now we've got neutral sp3 carbons, right? These carbons have no pi electrons associated with them. They have no charge. And so both of these compounds are non-aromatic products. Non-aromatic, non-aromatic. All right, so now the question we're asking ourselves is, what is the more favorable reaction? Is it more favorable to go from anti-aromatic to non-aromatic, or is it more favorable to go from aromatic to non-aromatic? So the clue is up here, right? Non-aromatic prefers to go to aromatic products. That's a favorable reaction. So the reverse reaction here is actually a favorable reaction. If the reverse reaction is favorable, that means that this direction, reaction B, is probably not that good, not that favorable of a reaction. But the opposite is true up here, right? In general, anti-aromatic starting materials will react very quickly, especially to form non-aromatic products. I guess if you could go from anti-aromatic to aromatic, that would be even more favorable, but usually that's pretty hard to do. You can't just rip electrons out of things, so, or add electrons to things. So in general, the chemical reactions that aromaticity really kind of controls are these two types of favorable reactions. Either we start with a non-aromatic product and we create aromatic, or non-aromatic starting material, excuse me. We start with a non-aromatic starting material and create an aromatic product, favorable, or we start with a very reactive anti-aromatic starting material, and that gets rid of the anti-aromaticity and makes a non-aromatic product. So these forces drive a lot of the reactions that we do in organic chemistry. A lot of any kind of cyclic compound, once you make it, has the potential to become aromatic or non-aromatic, and that can be a really strong driving force. And so you'll see a lot of examples of these types of questions. Why is this compound particularly stable? Why is this compound particularly unstable? which of these two reactions is more favorable? The answer to a lot of these ends up being about aromaticity, right? If aromaticity is involved, we want to make the aromatic products. We want to get rid of any anti-aromatic starting materials. And so that's a real driving force as we consider aromaticity in reactions.